Welcome to this podcast on architectural acoustics. In this podcast on simulation with pachyderm acoustics for rhinoceros, I will focus on another material property factor, the scattering coefficient, which can also be computed through pachyderm. In the previous podcast, we focused on absorption coefficients, and as mentioned, we will here focus on scattering coefficient. It must be noted, however, that this functionality or this method in pachyderm still is of experimental character, which means it is still in development. Nevertheless, let's try and see how this works and see what kind of data we get out of it. So what I'll actually do first is just I'll close this again, just model a simple geometry we can use for simulation. Remember to have your models in meters. So the geometry for the specimen geometry that you are interested in analyzing should be placed in 0, 0, 0. In this case, we just have a flat panel, which means basically you have close to nothing in 0 in scattering. So let's just give it a little bit of an angle to have a geometry that is slightly different than what is a flat panel. So what we'll do is we'll open the pachyderm acoustics software, and we will need to apply a material to absorption material as minimum to this material to be able to do the scattering coefficient analysis. So we'll just apply something here, it doesn't matter. Now we're just doing it for the test. So we so material on, and then we go into the hybrid models we have used so far for material definition, but now we need to look at the pachyderm time domain models. And in that we have 3 tabs: eigenvalues, scattering analysis, and visualization. And what we're interested here is the scattering analysis of this panel here. And what we see is that we have 2 different types of analysis. We have a correlation scattering coefficient, which is the one we're interested in for now, and we have the total scattered power. So we leave it at that, and then we can choose at what octave band we want to simulate or compute the scattering coefficient up to. So the higher you go, the more heavy the computational process. And I will also just remember to say here that it is a fairly intensive computational procedure, which will pull hard on your RAMs on the machine. Anyway, so let's just put it at 500 Hertz at the moment. Then you can set the sample origin. You can see already now it has found the center because we've placed it in 0, 0, 0. But otherwise, try to maintain 0, 0, and otherwise you can set the origin somewhere else. We then need to define the kind of the wall from around our specimen geometry here. So we say the dimension of the element is 1 meter, so the radius is 0.5. And the depth is perhaps 10 centimeters. So when we then click in the viewport, we will see now that we have a blue geometry that kind of encases our geometry. And then we have a dome geometry from which the sound is analyzed. So again, what we're interested in is to cover the geometry and then get the dome as close down as possible to the sorry. It's teasing with the commas and dots here, let's see. So, okay. Anyways, let's ideally this would be as close as possible, but let's maintain it at this level now and see if we can get things computed anyways. So now we have an encasement and we have a dome from which is where the source is located in terms of computing the sound. So then we're basically ready to compute the the scattering coefficient of this simple element here, which is slightly angled to the normal of the source. So I will simply press calculate now and see what happens. In the event that this will take long to compute, I will stop the recording and simply return, put it back on when we have a result down here. So, okay, we are back and we have now a scattering plot across the different frequencies. And what you can notice here is that I set it to compute up to 500 Hertz, but in that process I stopped it because why not compute the whole way? So instead I put it to 8000 and it computed for about 15 minutes on my machine. So now we have here plot for this setup with this geometry with quite low scattering coefficients, which is kind of obvious seeing the kind of geometry that we have been working on here for this podcast. So again, a brief podcast to show how to compute the scattering coefficients to be used in the definition of the scattering settings here as part of the material properties for setting up the simulation of a more advanced simulation. So in the time domain model, you can compute the scattering performance and scattering coefficients at different frequencies in relation to the geometry that you have designed. Thank you for watching this podcast on simulation and pachyderm acoustics for rhinoceros.